if you're watching my lectures in order in which I've recorded them, then we're taking a break from doing exponentials and logarithms to talk again about functions. And the reason why is because we need this concept of an inverse function to go further into logarithms. Turns out that the logarithm, as I've mentioned in the previous video, is the inverse of the exponential function, but that's easy to say, very difficult to understand. Now, if you're watching this independently and you don't know about a logarithm yet, that's not that big of a deal. There's only going to be a couple problems, not actually in this video, but in future videos that you'll encounter. But they're not major issues. You can ignore them. But at least in this part, the prereqs you have to know everything about functions, the notation, how to evaluate them, everything about the domain and range specifically. That's very important. And then you should also know how to graph objects, because I'm going to use a little bit, or I'm sorry, functions or whatever, because I'm going to use a little bit of graphing in this video. We'll start with the basic recollection of what a function is. It's just a machine that assigns to each input a single output. And so in this case, we'll use a machine diagram, and I have no idea why they call this the machine diagram, but it is the one that's been adopted. So let's say this is the machine F, and you get to plug something into it. So when I plug that object into this machine here, something happens to it. It gets transformed. You can't actually see into this box. Let's just pretend we cannot. And so something pops out, that whatever pops out we call f of x. And of course this is old news for us. We know that, if f is an equation, you plug in 3, you get out some manipulation of 3 that turns into, let's say, 10. Or you could have a machine that on an assembly line at let's say a car manufacturing plant, that puts windshields in. So what you do is you supply that machine with the car and the windshield, and out pops a car with the windshields installed. So that's kind of the idea of a function. One thing to note here is that even though a function assigns to each input a single output, the converse is not necessarily true. In fact, let's go ahead and take a simple example. So let's think of the function where our domain is given by this set of values here, this set of names, this group of names, and our range, in other words, our set of outputs, is those set of numbers. And those numbers will represent ages. So my function will be a of name. I'm going to plug in somebody's name and I'll get their age out. So let's go ahead and show what a possible mapping of this could be. Let's say Din is 37 and On is 13, and Jessica, let me give her a different color here so that you can kind of see, is 18, and let's pretend that Gerald is 22, Jose is 18, and Mark is I already have a couple black ones on there, so let me do blue here. Mark is 11. It's a little bit of a mess, but you can see what's up. So this is a function because if you input somebody's name, you get out a single output. Din's name responds with 37 years old. Mark's name responds with 11 years old, and Jose's name responds with 18 years old. However, if you gave me the output, which is the age, I could not possibly tell you who it corresponds to for some of these numbers, for one of these numbers specifically. I mean, okay, if you told me the age 37, I would be able to tell you, oh, that's Din. And if you told me the age 22, I'd be able to tell you, oh, 22, that's Gerald. And if you told me the age 11, I'd be able to tell you that belongs to Mark. And the age 13, I'd be able to tell you that belongs to On. But if you told me the age 18, 18 is the one that breaks that. 18 belongs to either Jose or to Jessica. Did I already mention Jose? All the colors look kind of weird to me. Oh, I'm sorry, Jessica. Yeah, Jessica and Jose. Yeah, I did say that right. I think I missed somebody, but that's all right. Anyway, 18 leads back to either Jessica or Mark. And so that's, or Jose. So that's an issue. I'll just highlight that on here because my eyeballs are not seeing it correctly. Okay. So this is a function, but this shows you that all functions do not have to have the quality where their outputs lead back to only single inputs. This is a perfect example of that. So think of a classroom that you're in. Everybody might have a different name, but a lot of people are the same age in a classroom. There's a lot of people around the age 20 to 22 in a college classroom. And this is where we really get to what we want in mathematics, which is a very specialized type of function, one in which all inputs lead to single outputs and all outputs lead back to single inputs. Well, let me give you an example of that. Let's suppose we adjust this example. Din leads to the number 38. On leads to number 13. That's her age. Jessica is 18. Gosh, that's the hardest one for me to follow. Jessica is 18. Gerald is 22. Jose is now 27. And Mark is 11. Okay? And in this case, if you said, listen, I want to know who is 37, I could tell you it's just one person. If you want to know who's 13, I could tell you it's just one person. It's on. So in this case, each of these outputs leads back to a specific individual. This is known as an invertible function. And this type of function is what we're looking for. Now, it's not always true that we can make a function invertible. In fact, a function is either invertible or it's not. There's just nothing you could do about it. If somebody hands you a function and it's not invertible, well, that's just the way it is. But if it is invertible, a lot of special things happen. Specifically, that we can undo things. So functions do things. Inverse functions undo those things. For example, in this case, the function takes a person's name and turns it into an age. But the inverse function, which goes in the reverse direction, takes the age as its input and returns the name. So that's what inverse functions do. They kind of undo. It's a circular kind of process. For a simple example, actually to go back to the machine diagram, let's take a look at plugging an object into our function machine f. And let's just suppose for a moment that f and g here, these two functions, these two machines that are going to work on an assembly line, suppose they're inverses of each other. What that means is I'm going to plug an object in to our function f. So here it goes. It just gets plugged in here. Now you can't see what happens in here. I'm not going to tell you what happens. It's just something. What pops out is an object that we call f of x, right? So it's some answer, some output. But we're going to take that output and plug it into the next machine. And remember, this next machine undoes that, right? So this next machine, when I plug this into it, it basically undoes everything that the first machine does. So what should pop out? Well, what should pop out is what we originally plugged into the first machine, x. This is what happens with inverse functions. They undo each other. So you could think of this is how I usually think of it, and this is how I've been talking about it the entire time I've been doing these lectures. This machine ties the knot. Let's just say ties the knot, and this machine would untie the knot. So if you're putting a shoe into this machine, this machine does something, out pops a shoe with laces all done up and knotted. And then you plug that in the next machine and it undoes all those knots and gives you back the original shoe. Okay? That's a great way to think about it because of the way that I've been doing these lectures, which I've been talking about. How do you undo addition? Subtraction. How do you undo multiplication? Division. Those are inverse operations. One does something, the other one undoes it. Let's make a current list of functions that we know and their inverses. And I put these in quotes because I'm not really going to use what people call function notation yet. I'm just going to use conceptual notation. So I'm just dealing with concepts in this video as much as possible, although we can't help but do a little bit of math. So, like addition. What undoes addition? Well, Subtraction. And same thing, if somebody hands you a subtraction problem, what undoes subtraction? Well, addition. Let's see, multiplication. Well, what undoes multiplication is division. And again, if they handed you division, what undoes division? Multiplication. How about squaring? Or no, let's do this. Let's take the square root of something. What undoes a square root? Well, squaring. Each of these are inverse functions. In a way. I mean, I'm not being super exact, but how about taking the cubed root of something? How do we untie that knot? Well, we cube. That's the opposite. And for those who've done logarithms and exponentials, if I gave you 10 to the x, the way you undo that is log base 10 of x. Okay, so these are kind of how you undo things. And again, I don't want to get too mathy, so I'm going to stop on the math topic right now and actually get into just a real world example where having an invertible function is super important. Now, Rsa Encryption is a special kind of encryption named after Rivest, Shamir, and Adelman. It dates back to 1978. Anyway, this encryption is very special because it's used in a lot of credit card transactions. And what it does is it's a coding scheme to help protect any type of information. It doesn't have to be just credit cards. It could be anything that you want to wrap up and hide from other people. So you would, it's the super decoder rings and stuff like that. You essentially change those values into other values. So letter A changes into something completely different, not a letter, but something completely different, and you send that to your friend, and your friend has a super decoder ring, and they decode that. So in essence, you have two machines going on. You have your machine where you take some type of information and you plug it into your machine, which is Rsa Encryption, and it encrypts it. It changes what it looks like. And out pops what looks like garbage to everybody else. Now, as that garbage is sent out and everybody can see that garbage, it's available for anybody, actually. Anybody can grab that. The only person that can decode it, though, is the person on the other end who's going to also get it. But millions of people can get this garbage if they want. This is actually how the Rsa encryption works. So when you send out your credit card information, it can be gotten, but it looks like garbage to everybody. Just a bunch of numbers. Okay, but what ends up happening is that the person who receives it is the only person really in the world that has this decoder. And so that garbage goes into that decoder and comes out of that decoder as the original information that you gave them. Pretty cool. So you put information into the coder, it turns out as garbage. You plug that garbage into the decoder, it returns back to the info. And look how circular this process is. I could take that info and plug it back into the coder, it turns back into garbage. I mean, you can go in circles here, right? But the idea is, if we didn't have an inverse function, if this was not invertible, that basically means that I take a message, code it, looks like garbage to everybody else, and then when you receive it, you try to decode it, and it comes out as something completely different. Not what I meant to say. Maybe it says, I absolutely detest you instead of you're hired, or something like that. Okay, so that's part of the reason why invertible functions are super duper important. You wouldn't be able to do credit card transactions on the internet. Now, that's a simplification of the Rsa encryption. I didn't even tell you how it's done. However, let me just tell you this. It is done using prime numbers. And you can't, well, I mean, it's theoretically possible to crack the code, but you would need a very long time. I think I had heard that if you set a computer on it to try to crack it and you didn't have the decoder, it would take you probably about 100 years. So by that time, you probably don't care about that credit card anymore. Another example, so that was our real world example. Here's a tabular example, because you often get functions that are given in tables. So our function f is described in this first table. It takes 2 and turns it into 10. It takes 3 and turns that into 12. It takes 4 and turns that into 14, and 5 and turns that into 16. Then here's another function, g. It takes 10 and turns it into 2. 12 turns that into 3, and 14 turns that into 4, and 16 turns that into 5. Notice that g undoes f. That is, everything that f did to turn 2 into 10, g undoes by taking that 10 and turning it back into 2. F took 3 and turned it into 12. Well, guess what? G turns 12 back into 3. And so on and so forth. So G and F are inverses. Something that I want you to also notice, what if I had listed this table backwards? And I said, oh look, we have a function G. 10, you plug in 10, it outputs 2. You plug in 12, it outputs 3, and so on and so forth. Would that change the inverse relationship between these two? And the answer is no, because for the function g, you plug in 10, you get out 2. Well, the function f will take that 2 and undo it back to 10. G turns 12 into 3, but f turns 3 back into 12. So they still undo each other. So f undoes g as well. And that's a big point to make. So if two functions are inverses, then it doesn't matter which machine you have it running first or which machine you have running second, because the fact is they undo each other. So if I let G run first and then F run, you'd get back to the original input, and the same thing vice versa. Also notice one last thing here. The inputs for one function become the outputs for the other. I know that I'm kind of repeating myself here, but this is going to be important. It's going to be a theorem we're going to write down in the long run, so I might as well just kind of give hints to it right now. So the inputs of one become the outputs of the other, and vice versa. The outputs of one become the inputs of the other. So like 2 is an output of G, and when that corresponding output becomes the input for F, returning the corresponding output. I know it's kind of weird to say, but 10 leads to 2, so 2 leads to 10. How's that? Okay. Which means essentially that the domains and ranges of these two functions swap. The domain of F is the range of G. Right? See these lists? Here's F right here. So see the list of inputs for F? That's the domain. And notice that happens to be the same list of outputs, or in other words, the range for G. Same can be said about the range. The range of F is equal to the domain of G. Right? Here's the range of F. F has the range 10, 12, 14, and 16. And G has the domain 10, 12, 14, 16. There you go. So that was a tabular example. Let's take a look at a function example. Here's two functions. I'm going to tell you right now that these are inverses of each other, but you want to actually find out if they truly are. One way you can at least test whether they're inverses or not is to build a table of values. X and f of x. And we'll over here have x and g of x. So in our first table, I'll plug in values like -1, 0, 1, 2, and maybe even a 3. -1 leads to -3 minus 2, or -5. 0 leads to -2. 1 leads to, well, 1 actually. And then 4, and then 7. Okay. So that's just me plugging in the values into the function f. Now G, I want to test whether these two are inverses by taking these outputs of f and making them my inputs of G. So -5, -2, 1, 4, and 7. Well, g of negative 5, that's equal to a negative 5 plus 2 over 3. That's a negative 3 over 3, which is a negative 1. G of negative 2 is going to be a negative 2 plus 2 over 3, which is 0. G of negative, G of 1, sorry. G of 1 is 1 plus 2 over 3, or 3 over 3, which is 1. And so you can see the pattern. This is going to be 2, this is going to be 3, because these, I could easily see G as the inverse now of F. At least this table implies it is true. So that's kind of the cool thing here, is that here I've shown that F and G are actually inverses. Well, I haven't shown it, but I've shown that it's likely to be true. By the way, I could easily have started with G and plugged in values. It's not that horrible if I did. Let's say I plugged in, I don't know, let's pretend I plug in 2, and I'll do this in red so you can kind of see it distinctly. If I plugged in 2 into G, I would have gotten G of 2 is equal to 2 plus 2, or in other words 4 over 3. 4/3, that's no fun, is it? Well, let's see what happens when I plug 4/3, that output, into what I consider to be the inverse function. So F of that output, which is now our input, 4/3. Let's see, that's 3 times 4/3 minus 2. The 3's cancel. 4 minus 2 is 2. And you see, I plugged in 2 to G, got out 4/3. I plugged that output into F, I got out 2. So they undid each other. I plugged 2 in, went through both functions, popped out back as 2. They must be inverses. There you go. But again, let me just reiterate, it's truly not a proof that these are inverses if you only take a handful of values. In reality, if you want to prove that two objects are inverses, you have to show that they undo each other for all values. And let me actually do that right now. I think that's a great idea. So I'll go ahead and let's see, I've opened a new page here, rewritten the functions. Now I'm just going to say, what if if you look at the machine diagram, I'll pause it and draw it in. There we go. And so what I want to do is I want to plug something in to F, something will pop out, and I want to plug whatever that is into G and see what pops out. What I'm really hoping it for is that whatever I plug into F turns out to be whatever comes out of G. So let's plug in just a very randomized number. Rather than choosing like 1, 2, or 3, let's just plug in the letter T. That's a good variable to say that we're going to plug in. So on the inside of the function actually takes T and multiplies it by 3 and then subtracts 2. That's what is happening on the inside of this machine. So out pops 3t minus 2. So most people don't get to look inside these machines, but we get to. So my phone rang and I don't know where I was. So let me just repeat something here. Sorry about that. But you have we're just going to plug in a random variable here, t. The function itself, normally we don't have the privilege of knowing what's going on inside a machine, but in this case they actually gave us the function. We know that it takes whatever we plug in, multiplies by 3, and subtracts 2. So out pops this business right here. Now what I want to do is check to see if G is the inverse. So what I'm going to do is take this output and plug that into G. Now this is where a lot of people have a difficult time because they don't realize how this works. So let me show you. Inside this machine, G, which is normally something plus 2 over 3, is going to do this manipulation. But what we're plugging into it is not x, we're plugging in this picture right here, 3t minus 2. So instead of x, I'll plug in 3t minus 2. Well, let's do this mathematics here first. So 3t, that was another phone call, a popular guy I guess. 3t minus 2 plus 2, that's just 3t in the numerator, divided by 3. 3's will cancel nicely, so this will become t. So I plugged in 3t minus 2, and it pops out t. Notice that I plugged in some random thing. I got out 3t minus 2, plugged that into the other machine, and out popped the original thing I plugged in. That means that G undid what F did. In other words, G and F are inverses. And this is really very general because of the fact that we are not dealing with actual numbers. We're dealing with a variable that we're plugging in, and it returned that same variable, which means had I plugged in 3 and gone through this process, the output at the very end would have been 3. Very neat. For our final example here, I want to take a look at a graph and its inverse. So we're actually going to build the inverse graph in this case using some information that we happen to know or can kind of guess at with inverse functions. So if I know this is a function and I've listed out the points, these ordered pairs, quite a few of them. I didn't actually have to list out that many, but whatever. It also goes through 0, 0. I didn't list that. But remember, if this is the function, its inverse will swap all inputs and outputs. In other words, the list of inputs in this table that I've just kind of quickly sketched here, they become the outputs. So the inputs swap to become the outputs, and those outputs will swap to become the inputs. In other words, these ordered pairs swap positions. And that's what I have in this table right here in black. So let's go ahead and plot these new points. Again, this is the x-axis, this is the y-axis. I didn't write it over on the first one, but I'll go ahead and do that right now, x and y. So let's see. -7, -8, that means backwards 7 steps and down 8. And I just gave up on kind of listing out the points. I have now successfully muted my phone so that I will get no other calls. All right, so I obviously did not write in the points here, but we're going to connect the dots, and this will be the graph of the inverse function here. I think that I miswrote something. Nope, it was perfectly fine. Okay, so when you look at this, you see that the graph of the inverse and the graph of the regular function are kind of similar. If you just tilt your head on the original function and kind of notice that, like I said, if you tilt this original function and flip it about the y-axis, it actually becomes this inverse function. Now, that's not really the point of this. All I wanted you to do is be able to graph the inverse, and we'll talk about more of the graph of the inverse later on. But it is kind of a neat idea that these two functions look very, very similar in a way. I mean, this one happens to be rising, where this one happens to be shooting off to the right, but they have something extremely similar in common. And here's my hint. It has something to do with these diagonal lines, which, by the way, the equations for these diagonal lines are just y equals x. Okay. Those diagonal lines are where the x and y values flip roles. In other words, if you look at this function right here, the input for this point is 8, the output's 7. This one, the input's 7, the output's 8. Notice our reflections about this line actually from each other. So this creates a mirror. This y equals x line creates a mirror that we can reflect about, and when we do that, we get the graph of the inverse. That's not what I want from this example. I just wanted to show you kind of how to graph the inverse. You just plot out a few points and then create the inverse table and plot those points. Now, the last thing I want to mention here before I leave is just to summarize what we've done here. We've just introduced something, an idea called the inverse of a function. And so that's a very special type of function that has an inverse. We call that an invertible function, a function whose outputs lead back to single unique inputs. That's called an invertible function. By the way, some textbooks title this a one-to-one function, although more commonly it's known as just an invertible function. But to be honest, you hear one-to-one function mentioned quite often as well. So one-to-one function means invertible function, and then less common but more advanced, it's also called a bijection. So it's that last word, bijection, is likely not held in very many or any intermediate algebra books that I know of. But it is true that it's called a bijection, a one-to-one function, or an invertible function. They all mean the same thing.